We have arrived at the 8th lecture of the series Bracket Algebra. First, the essential features of the previous lecture 7. For a set of kets, ket1, ket2, ket3, etc., consider the relation a1 ket1 plus a2 ket2 plus a3 ket3 plus etc. equal to 0. That is summation over I, ai, ket I equal to 0. If ai equal to 0 for all I, then ket1, ket2, ket3, etc. are linearly independent. If ai's are not 0, then ket1, ket2, ket3, etc. are linearly dependent. Consider a linear vector space with n independent directions defined by kets ket1, ket2, ket3, etc. Then any arbitrary ket psi, can be expanded as a linear superposition, ket psi equal to c1 ket1 plus c2 ket2 plus c3 ket3 plus etc. That is ket psi equal to summation over I ci ket I. Then the set of kets ket1, ket2, ket3, etc. is said to span linear vector space, and this relation is referred to as the expansion postulate. In a linear vector space, if a set of kets ket1, ket2, ket3, etc. happen to be linearly independent, that is summation over I ai ket I equal to 0, where ai equal to 0 for all I, and also span linear vector space, that is ket psi, which is any arbitrary ket, can be expanded as being equal to summation over I ci ket I. Then the set of kets ket1, ket2, ket3, etc. form a basis of the linear vector space. If in addition the inner product bra I ket j equal to Kronecker delta ij, then the set of kets ket1, ket2, ket3, etc. form an orthonormal basis for the linear vector space. We showed with example some important properties. Basis is not unique. There can be multiple bases for the same linear vector space. Linear independence does not imply span, and span does not imply linear independence. Note that we have been using the notation for basis, namely ket1, ket2, ket3, etc. That is, ket I is the typical component of the basis set. Obviously, notations can be changed and we can use the one that we like. Let us mention another popular representation where we express basis kets as ket phi 1, ket phi 2, ket phi 3, etc. That is, ket phi I is the representative ket, a typical component of the basis set with I running over 1, 2, 3, etc. Linear independence relation can be written as a1 ket phi 1 plus a2 ket phi 2 plus a3 ket phi 3 plus etc. equal to 0. That is summation over I ai ket phi I equal to 0, and this holds for ai equal to 0 for all I. That is a1 equal to 0, a2 equal to 0, a3 equal to 0, etc. Expansion postulate or span, or the principle of linear superposition, is expressed by expanding a ket, say ket psi, which is an arbitrary ket, as a linear combination of the basis kets. That is, it is equal to c1 ket phi 1 plus c2 ket phi 2 plus c3 ket phi 3 plus etc. In other words, ket psi equal to summation over I ci ket phi I, where ci is the expansion coefficient for the basis ket phi I. The orthonormalization relation is written through the inner product bra phi I ket phi j equal to Kronecker delta ij. Note that in case of linear vector space, the number of bases is fixed, that is unique, and this number is finite. Number of ket vectors in the basis set is called dimensionality of the linear vector space, which is finite. In fact, we have till now discussed only those linear vector spaces having finite number of independent directions, and its dimension, say n, is identified with the help of finite number of basis ket vectors, say 1 to n. Let us now explore what if the number of dimensions is infinity, that is n tends to infinity. So let us consider an infinite vector space. Infinite dimensional linear vector space has infinite number of independent directions. Infinite dimensional linear vector space cannot be described with the help of a finite basis set, an obvious statement. So we can give the definition of infinite linear vector space. If we cannot find a finite basis set to describe a linear vector space, we say that it is an infinite dimensional vector space. Let us ask a question. Is R3 an infinite vector space? To describe any vector in R3 3D space, we require linear combination of three non-collinear vectors. The number needed is 3, which is a finite number. So we cover or encompass R3 using three basis vectors. It might be I hat, j hat, k hat for example. So R3 is not infinite vector space, but it is a finite 3D linear vector space. The three basis ket vectors ket phi 1, ket phi 2, ket phi 3 are able to span the entire linear vector space R3. We are well on our way to define and describe what is called Hilbert space. Let us consider the linear vector space, the Rn space, where n is a finite number. An element in this linear vector space is a ket vector, ket phi, represented by a column matrix, the column x1 up to xn. The corresponding bra is a bra phi, which is ket phi dagger. That is the dagger of the column x1 up to xn. So it is a row matrix x1 star up to xn star. With the help of the ket and the bra, we can form the inner product defined through the relation bra phi ket phi equal to row matrix x1 star up to xn star multiplied with the column matrix x1 up to xn. And this generates a number mod x1 square up to mod xn square. Now bra phi ket phi equal to summation over I mod xi square. The length or norm of phi is given by under root sum of squares. Let us make the space Rn to be infinite dimensional by putting n tending to infinity as a limit. So we shall replace n by infinity. Now the length or norm of ket phi is, so the norm is equal to under root summation over I from 1 to infinity mod xi square. In quantum mechanics, we deal with state vectors represented by ket vectors, and they should be well defined. This is an obvious and legitimate demand. The ket vectors cannot have arbitrary length, that is norm. In other words, they cannot have infinite length. We deal with vectors of finite length so that we can perform various operations. Indeed, we cannot handle infinitely large numbers because their addition or other operations lead to nowhere. We do not get a finite result that we can write down neatly. And so we have to ensure that things do not go out of hand and become arbitrary or undefined or anything or infinite. The result after calculations should be necessarily finite so that we can lay our hands on them, write them down. Hence, the summation over squares appearing in the norm should be finite. The infinite series should converge. In other words, the infinite series should be summable, should give a well-defined result. That is, the norm should be, let us write it clearly, summable, finite, should converge. Such a linear vector space is called square summable, and the linear vector space is denoted by small l square. we make a gist. Linear vector space is denoted by small l square and called square summable if the norm of a ket vector is finite, even if it involves an infinite series sum. In quantum mechanics for microsystem, we cannot make certain or definitive or deterministic statements because of inescapable uncertainties in observables, this being an inherent feature of the law of nature and addressed in quantum mechanics. As things are not definitive but uncertain, quantum mechanics makes probabilistic predictions. We speak in terms of probabilities, that is, make probabilistic statements. The probability scale is defined by setting total probability equal to 1. Probability is defined in terms of state vectors as denoting state vector by ket psi, the inner product of bra psi ket psi, which is an integration from minus infinity to plus infinity psi star of x psi of x dx, that we can write as integration from minus infinity to plus infinity mod psi square dx. Of course, we are doing things in one dimension, where bra x ket psi is defined as psi of x, which is called wave function, and this is the expression of probability in terms of wave function. The integrand involves square of wave function psi of x. Here it is. To proceed further with the integration, we should be able to integrate, that is, put in a different language, the square of wave function mod psi of x square should be integrable, that is, wave function psi of x should be square integrable. This is a legitimate demand because if we fail to integrate, we will not be able to determine probability and quantum mechanics will fail then. Such a linear vector space is called square integrable and denoted by capital L square. Let us make a gist. The linear vector space is denoted by capital L square and is called square integrable if the wave function psi of x is such that we can perform the integration that involves square of wave function. In the linear vector space, when we come across infinite summation or integration where the limits involve infinity, maybe the integration is from minus infinity to plus infinity, then the sum or the value of the integration, that is the result of calculation or any mathematical operation, should fall in the linear vector space that we are considering, so that we are able to find them, deal with them. Things are then finite, bounded. That is, the result should not be out of bounds or unreachable. Only then we can successfully deal with state vectors. Such a linear vector space is called complete linear vector space. The criteria is mathematically expressed in the works of Cauchy and is referred to as Cauchy sequence. Let us just mention Cauchy sequence. Consider state vectors ket psi 1, ket psi 2, ket psi n, ket psi m, and so on and so forth. As n tending to infinity, m tending to infinity, ket psi n and ket psi m should converge and the difference in length should shrink to 0. This can be written as also the difference of the state vectors ket psi n and ket psi m should give a null ket vector. In the limit of infinite n and m, this is possible if for n tending to infinity, ket psi n is equal to some limiting ket psi, and for m tending to infinity, ket psi m is also equal to the same limiting ket psi. Here ket psi is the limiting state vector. If this is so, then under the limit n tending to infinity, m tending to infinity, ket psi n minus ket psi m equal to ket psi minus ket psi equal to 0, this 0 being the null ket. If the limiting state vector ket psi is a member of the linear vector space we are considering, we then say that linear vector space is complete. Let us make a gist. Finite dimensional linear vector space is automatically complete. Everything is well contained and hence complete. Nothing beyond our reach, and this is an automatic feature in a finite dimensional linear vector space. Infinite dimensional linear vector space has to be made complete. This is done by imposing the restriction that it also contains the limit, say ket psi, of any state vector like ket psi n for n tending to infinity. So everything is made to fall within the region, the linear vector space, where we would work. Here, in an infinite dimensional linear vector space, we have to achieve it, ensure it. Things are not automatic in general as in a finite dimensional linear vector space. The time is perfectly ripe, or we would say that the stage is set for us to define what Hilbert space stands for. In quantum mechanics, we deal with state vectors, which is defined in a space that is a linear vector space, which is infinite dimensional. We do not want to leave out any direction out of the purview of our discussion. This is a complete linear vector space. Even the limiting values are contained reachable. That contains inner products. This allows us to give a physical meaning to the abstract theory where we are dealing with bra-ket state vector, infinite dimensional complex linear vector space, etc. Because through inner product we can define physically meaningful quantities that we can measure in experiments like average of position, average of momentum, etc. Also, quantum mechanics speaks through probabilistic language, and probability involves inner product. So such a space is called Hilbert space, an abstract space that allows calculations, but after calculation we get physically meaningful quantities. Operation in Hilbert space ensures that calculations are performable even if space is of infinite dimensions. Calculations are error-free and rigorous. We have to further brush up a little bit the Hilbert space for us to work with quantum mechanics hassle-free, that is without any trouble. So we need to define separable Hilbert space. In quantum mechanics, we use a Hilbert space that is described by a basis set, the members of which are countable. We can separately count the bases like ket phi 1, ket phi 2, ket phi 3, etc. and it goes on. Such Hilbert space is called separable Hilbert space. In quantum mechanics, we use that Hilbert space where wave function psi of x can be normalized such that state vectors have a fixed value of length. We take it to be unity. The normalization condition is bra psi ket psi equal to 1. We can sandwich a unit operator between bra psi and ket psi and then replace the unit operator by. This gives us, and we use the fact that bra x ket psi is the wave function psi of x, and also that bra psi ket x is the dagger of bra x ket psi, which is a number, and dagger of a number is simply the complex conjugate of the number. So we have bra x ket psi star, which is nothing but psi star of x. Putting them in proper place, we end up with, which can be rewritten as, this is needed to be square integrable. This is the condition or restriction. Let us mention that we use a Hilbert space where wave function can be normalized even if it is not square integrable, that is, even if the integration shoots to infinity. Things are not allowed to go out of hand really by use of Dirac delta normalization technique. where wave function is normalized to Dirac delta function by putting bra k ket k prime equal to Dirac delta k minus k prime, where bra x ket k is defined as the wave function psi of x corresponding to k. What is k? K occurs in the famous relation p equal to h cross k that leads to k equal to p by h cross. Here p is momentum, h cross is h by 2 pi and h is the Planck's constant. Now we can sandwich a unit operator between bra k and ket k prime to get, and instead of the unit operator let us write bra x ket k prime as the wave function psi k prime of x, and bra k ket x is the dagger of bra x ket k, which is psi k star of x. This leads to integration minus infinity to plus infinity psi k star of x into psi k prime of x dx equal to Dirac delta of k minus k prime, which is the Dirac delta normalization relation through which we have avoided direct occurrence and interference of infinity in our calculation. Normalization in this case, and we can now proceed without any divergence. We shall be addressing the question, what is triangle law, in a future lecture.